Good morning, good afternoon, and good evening, everyone. I'm Araki, Osaka University, Japan. I'll be talking about evaluation of hydraulic performance of wave dissipating block using porosity. This is the table of contents of my presentation. First, I'm going to talk about introduction, background and aim of this study. Next, I'll explain the experimental setup, wave dissipating blocks, rubber mound structures, and measurement. After that, I will show some of the measured results and discuss them. Lastly, I will conclude my presentation. Introduction. The hydraulic performance of wave dissipating block mainly depends on its shape and porosity. Particularly, the porosity of wave dissipating block is strongly related to the amount of concrete. If the wave dissipating blocks with larger porosity are used, the construction cost can be reduced due to smaller amount of concrete. However, the effect of the porosity of wave dissipating blocks on hydraulic performances such as reflection and transmission has not been investigated sufficiently. The aim of this study is to investigate the influence of the porosity of wave dissipating blocks on the reflection and transmission coefficients. Experimental setup. A series of experiments was conducted in a two-dimensional waveflume shown here. We generated irregular waves with the target spectrum of modified Brett-Schneider-Mitzias spectrum. The significant wave height at rubber mound structure was between 0.04 and 0.12 meter, and the significant wave period was 1.2, 1.5, 1.8, and 2.1 seconds. No significant wave overtopping was observed, except a few cases. No significant deformation in the profile of the rubber mound structures was also observed. Water surface elevations in front of and behind the rubber mound structure were measured at the sampling rate of 20 Hz for about 200 seconds. Reflection and transmission coefficients Kr and Kt were estimated from the measured water surface elevations. We measured the water surface elevation and estimated the reflection and transmission coefficients twice under the same condition. We took the average of them. The depth at the two of the rubber mound structure was 0.3 meters. We used four kinds of wave dissipating blocks: Tetrapod, Doros 2, Doros, and Tetraneo. The porosity of these blocks, lambda, is 0.5, 0.51, 0.575, and 0.6, respectively. The profiles of the rubber mound structures are shown here. Tetrapod, Tetraneo, Doros, and Doros 2. The dimension of the rubber mound structures was determined by the design standard in Japan. Each rubber mound structure had no core, and the main part of the structure was composed of only wave-dissipating blocks. These are photos of the rubber mound structures for each block. We estimated the reflection coefficient Kr using Goddard's method as the square root of the ratio of the reflected wave energy to the incident wave energy. We estimated the transmission coefficient Kt as the ratio of the significant wave height behind the rubber mound structure to the significant wave height measured at the same position without the rubber mound structure. Results and discussion. The reflection coefficient Kr for the wave dissipating block with larger porosity is generally smaller. The vertical axis of this figure shows the reflection coefficient Kr, and the horizontal axis shows the surface similarity parameter. In the figure, red, green, black, and blue show the reflection coefficients for Tetrapod, Dolos 2, Dolos, and Tetraneo, respectively. The black solid line, this line, shows the reflection coefficient estimated by the equation proposed by Dr. Zanutihi and Dr. van der Meer for reference, shown here. The reflection coefficient for the wave dissipating block with larger porosity is smaller among Tetrapod, Dolos 2, and Tetraneo, red, green, and blue. However, the reflection coefficient for Dolos, black circle, was smaller than the reflection coefficient for Tetraneo, blue, although the porosity of Dolos is smaller than the porosity of Tetraneo. It is possibly because the shape of Dolos is more complicated, but it is still under investigation. The transmission coefficient Kt for wave dissipating blocks with larger porosity was generally larger. The vertical axis of this figure shows the transmission coefficient Kt, and the horizontal axis shows the wave steepness. In the figure, red, green, black, and blue show the transmission coefficients for Tetrapod, Dolos 2, Dolos, and Tetraneo, respectively. The solid lines in the figure, red, green, black, and blue, shows the transmission coefficients estimated by the equation proposed by Dr. Takeda et al. This equation includes the effect of the porosity, the surface area, and the volume of each block, and the width of the structure on the still water level, as well as the wave steepness of the incident wave, shown here. The transmission coefficient for the wave dissipating block with larger porosity is larger among Tetrapod, Dolos 2, and Tetraneo, red, green, and blue. However, the transmission coefficient for Dolos black circle is as small as the transmission coefficient for Dolos 2 green, although the porosity is very different. It is also possibly because the shape of Dolos is more complicated, but it is still under investigation. The equation proposed by Dr. Takeda et al. Approximately estimated the measured transmission coefficients for tetrapod, Dolos 2, and tetraneo, red, green, and blue. Unfortunately, the equation considerably underestimated the transmission coefficient for Dolos black circle. However, the equation provided a relatively smaller transmission coefficient for Dolos in spite of larger porosity of Dolos. Conclusion. The reflection and transmission coefficients Kr and Kt for the wave dissipating blocks with larger porosity was smaller and larger, respectively, among Tetrapod, Dolos 2, and Tetraneo. The reflection and transmission coefficients for Dolos were both smaller in spite of larger porosity. The measured transmission coefficients for Tetrapod, Dolos 2, and Tetraneo were approximately estimated by the equation proposed by Dr. Takeda et al. This is acknowledgement. Thank you very much.